We are about to find all the zeros to an equation. Before we do that, never forget, zeros and roots are the same thing. They are also the same things as x-intercepts, and they are the solutions to an equation. Never forget. Put that up there, and let's see what we got here. Also, this is worth looking at quickly. All the numbers known to us at this point in time are the complex numbers. Okay? Of those complex numbers, they're broken into real numbers and imaginary numbers, and then reals are broken down further. What I want you to keep in mind are rational numbers are real numbers. When we're finding rational zeros, we're actually finding real zeros as well. Okay, let's make that a little smaller. And now, here's a suggested plan of attack. This will help us figure out all the zeros. First, we're going to use Descartes' rule of sign. We can figure out how many positive real and how many negative real. If it's a fourth degree polynomial, then we know for a fact we have 4 complex roots. So if we know we have one of these and one of these, well, then that would guarantee us that we have 2 of these. It helps us. What we're going to do then is we're going to use that rational root theorem. You can also call it the rational zero theorem. That's going to give us a bunch of possible rational zeros. Again, we're dealing with infinitely many numbers. That narrows it down to, say, 16 or so. Once we have it down to something like 16, I can then take all those values and plug them into our function. If it equals 0 and we plug it in, then it's an actual rational zero. Again, we call them zeros because it makes our function equal 0. We are then going to divide those roots out. Once we divide those roots out, it depresses it down to a second-degree polynomial. Well, that's our goal, get it down to an x squared. Once we have it down to an x squared, then we can do our last part, d. If it factors nicely, great. Then just do so and find the last 2 zeros. If not, complete the square or quadratic formula, and that'll get them for you. I recommend pausing this for a minute to get these down in your notes before you do the examples. Let's find all the roots to this polynomial equation right here. We are going to begin with this gentleman's rule of signs, and let's do that. Descartes' rule of signs. This is our f of x, and let's see how many sign changes in our f of x. Okay, this is our f of x. We're just setting it equal to 0 here because we're trying to find the zeros, and that's what you do. So our sign changes. That's positive. We have 1. Nope. 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 We only have 1 sign change, which means we're guaranteed to have 1 positive real root. Okay, that's good to know. How do you find the negative reals? Well, you plug in a negative x. Well, if we were to do that, that would give us this. We would have a negative x to the 4th minus a negative x to the 3rd minus a 2 times a negative x squared minus 4 times a negative x and minus 24. Well, let's see what would happen. That would give us, this would be a positive x of, now I want to do this, hold on, black. That would give us a positive x to the 4th, and this right here would be negative, and negative times this would be, let me write it down here, we have a positive, then this would give us a negative negative, which is a positive. Over here, negative times a negative is a positive x squared, but positive times this negative 2 is negative term. Negative x times negative 4 is positive 4x. And we have a negative 24. Those are our new signs. No change, 1 change, 2 change, 3 changes. We have 3 or 1 negative real roots or zeros. Okay? Based on the counting. All you do is count. It's going to be that or 1 less. I'm sorry, 2 less. So now if we were to look at this complex list here, we have positive real, negative real, imaginary. Now let's see what we got. Here are our choices. We know we're only going to have 1 positive real root, no matter what, 1 of them. Well, we could have 3 of these or 1 of these, so we could have 3 of these or 1 of these. Well, if we have 1 positive real and 3 negative real, and this right here, this 4 tells us that we only have 4 complex roots. Well, if we have 4 real roots, 1 positive, 3 negative, that means we have no imaginary. Well, no matter what, we only have 1 positive real root. This right here tells us we have 1 positive real root. So no matter what, we have 1 positive real root. Well, if we only have one negative real root, that means we have two reals, means we have to have two imaginary. All right, so that's what we're looking for. Next, we're going to use the rational root theorem or the rational zero theorem to find some of these roots. So again, we have plus or minus p over q. The factors of this number are our p. The factors of this number are our q. If you don't see a number, it's 1. Okay, well that means that we have plus or minus a whole bunch of numbers. So I like to do this. And let's see, so it's p over q. It's in this format right here. So for our 24, we can either have plus or minus 1 times 24, plus or minus. Everything is plus or minus. Because you could either have plus plus times minus minus, or you could have minus plus times plus minus. So you get every outcome. So it's 1 times 24. It could be 2 times 12. It could be 3 times 8. It could be 4 times 6, and I think that's all we have. So there we have it. And our q, well, q is our denominator, but in this case it's plus or minus 1. So just putting all these, all over 1, you're still left with the same integers up above. So we have, let's see what we got. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 times plus or minus. We have 16 numbers out of all the numbers now to choose to see which ones are real or rational zeros. Alright, scratch those last few seconds, technical difficulties. This is what I was trying to get across. We have a function, and we're going to take these 16 numbers right here, and we're going to plug them in, and we're going to say which ones make them equal 0. If it equals 0, it's a root. So now we plug in these numbers, okay? You do this in a calculator, save yourself some time, and you plug in all these roots. We had 16 of them. So the ones that come out to be roots are these two. If you plug in negative 2, you get a y value of 0. If you plug in positive 3, you get a y value of 0. You have two roots. You have a root at x equals negative 2, and you have a root at x equals positive 3. Okay, so here we go. We now know we have one positive real and one negative real, and we're trying to find the last two imaginary roots. So what we're going to do is this. We're going to take those roots and we're going to divide them out. I'm going to use synthetic division. Okay, I've shown you options. You have options available to you. Synthetically is what we're going to do now. So I'm going to start with our first root, x equals 3. Remember, when you're using synthetic division, you want the root out there anyway, so 3 is what we want. We're going to divide it out of this polynomial right here. Our coefficients are 1, negative 1, negative 2, negative 4, and negative 24. Let's see what happens. We bring down that 1 and we multiply 3 times 1, we get 3. We add up that column, we get 2. We multiply that 2 to the 3 and we get 6, and we put that there. We add up that column, we get 6 minus 2 is 4. 4 times 3 is 12. 12 minus 4 gives us 8. And then we multiply that 8 to the 3 and we get 24. And like I would expect, we add that up and we get a remainder of 0. Okay? Because you're dividing at a root, the remainder should be 0. Which leaves us with this depressed polynomial. We now have an 8. We have a 4x. We have a 2x squared. And we have a 1x to the third. Okay? All right, well, that's our depressed polynomial, but we're going to depress it even further. We're going to divide out the next root, that negative root, negative 2. So if I do that, let's change the color. We're going to divide the negative 2 out now out of this right here. Okay. So again, I'm going to use the coefficients, which are 1, 2, 4, 8. And we bring down the 1, and we multiply negative 2 times 1, we get negative 2. Add up the column, you get 0. 0 times negative 2 is 0. We add up 4 and 0 and get 4. 4 times negative 2 is negative 8. And this right here gives us a remainder of 0. Which leaves us with a constant for a 0x and a 1x squared. Which is really the same thing as this. We have x squared plus 4. Alright, well, if we want to find the zeros, I could set this equal to 0 and see what happens. I could do this. I could move the 4 over. You could use the quadratic formula too. Just if you do that, remember your b coefficient is 0. But at this point, I could do this. Take the square root of both sides, and that's going to give me x. and this is going to give me plus or minus the square root of 4 times the square root of negative 1. Don't forget, this is the same thing. Well, that gives us this. X equals plus or minus, that's a 2, and this is an I. So there are our two imaginary roots. We have x equals 2i and x equals negative 2i. Okay, there are two imaginary, there are two real, one positive, one negative. All right, let's try this guy now. Fourth degree, but now we have an 8 and we have a 3. So let's start off like we did before and figure out how many of each we have. So for the positive reals, we got to do this. And that's going to be a positive 8, which is 1, 2, just 2. So that's going to be 2 or 0 positive real roots. Excuse me. Positive real roots or zeros. Don't forget roots or zeros. Okay, for the negatives, plug in a negative. And that's going to, let's see, that's going to stay positive here. That's going to change to positive. That is going to stay positive. That is going to change to a negative, and that will stay a positive 3. So that's going to be no, 1, 2. Two sign changes. We have 2 or 0 negative reals as well. All right, now that gives us a little bit more variety than we had before, which doesn't change the complexity of our problem. It just changes the number of choices we have. And this is what I mean. Let me do that. Okay, so again, we're either going to have positive reals, we're going to have negative reals, and then we have imaginaries. These comprise all the complex numbers. Okay, and we have 4 of them. So here, I'm either going to have 2 or 0 of these, right? But guess what? I'm also going to have 2 or 0 of these, which gives us more choices than just 2 choices. Because I'm either going to have 2 positive and 2 here, these are negative. I'm either going to have 2 positive real and 2 negative real, or I could have 2 positive real and 0 negative real. Down here, if I have 0 positive, I could have 0 negative, but if I have 0 positive, I could also have 2 negative. 0, 2, which gives us more choices. That's it. All right, well, again, we always have to have 4 complex roots. So if we have 2 positive and 2 negative, we have to have 0 imaginary. If we have 0 positive and 0 negative, guess what? We have to have 4 imaginary. They always add up to be 4, so we have 2 positive, no real. That has to be 2 of these and 2 of these. Hopefully that's starting to make sense to you now. Let's make that a bit smaller. Let's move on. Let's find the possible rational roots. Well, for those, we have, here is our P and here is our Q. So for our P's, again, it's plus or minus P over Q. The P's, we could have, well, it's either going to be a plus or minus 3 or a plus or minus 1. And then, well, the bottom, the Q's are 8, so that's either going to be plus or minus 1, plus or minus 8, plus or minus 2, times plus or minus 4. So let's just simplify this mess. I always tell you, I put the plus or minus on the front. I think it's so much easier. So we're either going to have this combination. We're either going to have 3 over 1, 3 over 2, 3 over 4, or 3 over 8, plus or minus. And then the same thing for plus or minus 1 over 1, plus or minus 1 over 2, 1 over 4, 1 over 8. Those are our choices. So let's write it out. We have plus or minus 3 over 1, 3 over 2, 3 over 4, or 3 over 8. We could also have 1 over 1, or 1 over 2, or 1 over, what am I doing, 1 over 2, 1 over 4, or 1 over 8. Okay? So that gives us what? 1, 2, 3, 4, 5, 6, 7, 8. 8 times plus or minus. We have 16 numbers we have to choose from now. In the interest of time, we are going to plug in these 16 values, again, into our f of x. And our f of x, again, was right over here. Okay, you should have that in your notes. And we are going to plug those in and get, here, let me do this. When x equals negative 1/4, we get a 0. and when x equals positive 3/2, we get a 0. Okay, so it's going to be the positive 3/2, and the negative 1/4 is where we'll find roots. Okay. We are going to take those roots, negative 1/4 and 3/2, and divide them out. After we divide them out, we're going to have an x squared. So here we go. And let's change this to red. All right, so the first one, it doesn't really matter. I'll just do negative 1/4. And we're going to divide that out from our function over here, which was an 8. And then we have a negative 26. And then we have a positive 9 and a 16 and a 3. We bring down the 8. We multiply. That's going to give us a negative 2. We add that column up, we get a negative 28. We multiply that and we get a negative 28 over a negative 4, which is a positive 7. Add that up, we get 16. 16 times negative 1/4 is negative 4. Negative 4 goes there. Add up this column. 16 plus a negative 4 is a positive 12. We multiply this 12 times that, and we're going to get negative 12 over 4. Negative 12 over 4 is negative 3, and that's going to add up to be a 0. Again, this is our remainder. This is our new polynomial. I'm just going to leave that because those are the coefficients we need to use now to take 3/2 and divide out. Okay, so we're going to divide out 3/2 now. We bring down that 8. 8 times 3/2 is 24 over 2, which is 12. Add that up, you're going to get a negative 16. We multiply negative 16 times 3/2, that's going to be negative 48 over 2, which is negative 24. 16 and a negative 24 is a negative 8. Negative 8 times 3/2 is negative 24 over 2, which is negative 12, and 12 minus 12 is 0. We have another remainder of 0. We're also left with this polynomial. We have 8x squared minus 16x minus 8. Don't forget this was our remainder. Okay. Now before we go ahead and jump in with our quadratic formula, we can easily make our number smaller. I have an 8, a 16, and an 8. If you can make your number smaller, why not? I'm going to take out a common factor of an 8, which is going to leave me with x squared minus 2x minus 1. And we divide that by 8. 0 divided by 8 is still 0. And that right there is a much easier polynomial. In fact, I think we might even... no, it's not going to factor nicely. Oh well, let's do this. X equals negative b. Here's my b, here's my c, here's my a. A is 1. So I have a negative b, negative 2 is 2, plus or minus the square root of b squared, which is a positive 4, negative 2 times negative 2, minus 4 times a times c, all over 2a, 2 times 1. That's going to give us 2 plus or minus the square root. Let's see what we got here. If we multiply all this, we get a positive 4, and 4 plus 4 is 12. Psych, 4 plus 4 is 8 over that. All right, let's simplify this. Let's see if we can get this a little bit down here. So we have, let's start right there. And I'm going to change this to blue. So we have x equals 2 plus or minus, how do we simplify that? Well, we have the square root of 8. That could be the square root of 4 times the square root of 2. This is 2 radical 2. 2 radical 2. All over 2. Which can be also thought of as this. This is x equals 2 over 2 plus or minus 2 radical 2 over 2. And that equals 1, and that equals 1. So we could also say that x equals 1 plus or minus radical 2. Ta-da! There are all our roots. We just found, here, let me change this to green so it'll stick out. So we have x equals negative 1/4. We have x equals positive 3/2. We have x equals 1 plus radical 2. And we have x minus 1 radical 2. There are all our roots. And just like we did here, finding all the zeros, we're going to practice this in class. Where are we? Right here. Do day 7. See you then.